when you get into, or if you get into like physics, calculus-based physics, if that's a direction that you're going to in college, you'll work with the derivatives. It tells you like acceleration, and the third derivative is jerk, and velocity. All of these derivatives tell us something different in the movement of planets or rocket ships or whatever it is we're looking at. For us, our derivatives in math tell us how things are changing and how things are moving graphically. And so my first derivative, the first derivative tells us extreme values. I just write them as mins and maxes. My second derivative tells me points of inflection. And a point of inflection is simply where a graph changes concavity. So a point of inflection. If I have a third powered function, here's my cubed function. And right at this tippy top and this low point here, that's where the first derivative equals 0. Okay? But in between this curve, where it changes from opening down to opening back up, that's the point of inflection. I'm going to do that on mine in a different color. This point is a point of inflection. And that happens when the second derivative equals 0. So I'm going to do almost the same thing I did yesterday, except because I'm finding something different, my interpretation is different. So when I am looking at this, I am going to find my first derivative and then find my second derivative. I'm going to set my second derivative equal to 0. I will find the x value that occurs at, and then I'm going to make a double prime table to see what's happening on either side. But it's not increasing or decreasing on either side. What it is concave down and concave up. Inside here, up until this point, that is in that region, concave down. Because it is opening down. In this other region, after that point of inflection, right inside there, that's where it's concave up. And so when we talk about concavity, concave up or concave down, what I do is I just interpret that as an interval. From the far left up until that point of inflection, it is concave down, and then from that point of inflection all the way to the far right, it is concave up. And so our answer is not going to be a point, it's going to be an interval. So let's jump in and start it out. First derivative. F prime of x is 3x squared minus 6x. Second derivative, 6x minus 6. I'm going to set that equal to 0 and solve and make a double prime chart. And I'm slowing down and letting you get caught up. All I did was found the second derivative, set it equal to 0, made a double prime chart. I still want to check on each side what's happening. And I'm going to check it in my second, where my second derivative is 0. Same way I did before. I do test points. To the left of 1. Give me a number to the left of 1.
0.
0. When I put 0 in here, what do I get? Negative value. So this is negative here. That means it is negative all the way through here. Negative, don't mistake this for increasing and decreasing. This means when I look at the second derivative, because it's negative, it is concave down. Now I'm not looking at what's happening. It is negative. That means the graph is opening down in that region. Then I move to the next one. Other side of 1. Give me a value. Plug it in. Positive. That's a positive region. That means everything over on this side, no matter what number you picked, you could pick 3, you could pick 10, you could pick 100, no matter what number you put in here, it's always going to result as a positive. You could even pick 1.00001, because it's to the right of 1. It will come out positive. That means everything in that region is a positive region, and I interpret that as concave up. So I'm reading this differently when I'm using the second derivative. The first derivative, I'm looking for increasing and decreasing. The second derivative, I'm looking for opening up and opening down. And so when I write my answer, I say, from the far left, and I always do everything, I read it from left to right. From the far left, this is my foreign language of math, up until 1, this graph is concave down. But from 1 to the far right, this graph is concave up. And that is my final answer. Any questions? Okay. The second derivative of a cubed function. The first derivative is squared. The second derivative is linear. Linear functions will only have one x value. When I work with a higher power, like a fourth power, think about what a fourth power looks like. It could be this, or it could be this. I have 2 places where it changes concavity. Potentially. Remember, that doesn't mean it's exactly going to do that, but I have 2 points of inflection. I have 2 mins and a max, or 2 maxes and a min, and then 2 places where my concavity changes in each of those graphs. If there are twists, I won't necessarily see that as much. But remember, my interpretation is not decreasing and increasing anymore, not finding high points, low points, but finding where that curve is changing its direction. So f prime, 4x cubed minus 8x, f double prime, 12x squared minus 8, set it equal to 0. I'm going to pull out a 4. I could factor this as a difference of squares. This is the square root of 3x plus the square root of 2 and the square root of 3x minus the square root of 2, that's a really ugly difference of squares. So my other alternative is to take both my factors and set them equal to 0. When does 4 equal 0? Never. But I can definitely solve for the 3x squared minus 2, add the 2, divide by 3, take the square root, don't forget plus and minus, rationalize the denominator, multiply the top and the bottom by the square root of 3. And now this kind of icky looking number is the point where this is going to change from concave up to concave down. I just need to figure out which one it is. So this is my point of inflection. Don't be afraid of kind of ugly points. Because remember, all we need to do, oops, got to write that correctly. All I really need to do is get an idea of where it is and plug something on either side into my second derivative. So can somebody help me out? Give me an about-sies on the square root of 6 divided by 3. Bless you. 0.82-ish. Anybody want to agree with that? You agree? Great. So that gives me just an idea of what values I should be plugging into my second derivative. So give me something to the left of negative 0.82. Negative 1. So the 4 is always going to be positive, and then I'll plug negative 1 in here. So I square negative 1, it becomes positive 1. I multiply it by 3. And then I subtract 2. And it looks to me like it's positive. Sometimes if I can, I'll go even like obnoxiously over. What if I put in something like negative 10 or negative 100? Well, I'm going to square this and it's going to get really big, and when I subtract 2 from it, it's going to stay positive. So it's real easy to visualize. Times another positive. This is a positive region. Positive region. I interpret that as concave up. Positive region here is not a min or a max, not increasing. That's where it's concave up. That means the graph is opening up here. Then I'll do a middle. Give me a betweensies. 0 is a super easy one. I get a positive 4, and I end up with negative 2. Negative region, concave down. Yes, I get lazier as I move on. I'm CONC instead of writing the whole concave. Pretty soon it's just going to be CD and CU. Okay, and then I'll do my last region again. 10, 100, 1, or yeah, 1 would work. Either way, it's positive and positive, another positive region. And so again, it's concave up. And so I need to interpret this into my answer. I start from the left. Always start from the left and work your way over. So, from the far left up until I hit negative square root of 6 over 3, I am concave up. And then from negative square root of 6 over 3 up until I hit square root of 6 over 3, I am concave down. And then from the square root of 6 over 3 up until positive infinity, I am concave up again. Sometimes they'll write this double thing as, this is just another way to write it. I would say from negative infinity up until negative square root of 6 over 3 with, that's my little with, including the square root of 6 over 3 up until infinity, it is concave up. So in both of these regions, that is what's happening, okay? Do you have to write it that way? No, again, I just like to show you things that you could see. Maybe it'll be listed this way. If you want to just do like I do and go from left to right and write your answer that way, it's very organized, feel free to do it. How do you guys feel about this? Doable? Okay. Do we do any more? Think you got it? Why don't you guys show me you got it and do number 4? Okay, I'll pause here. You can do number 4. We're not going to get into the fifth powers. Again, not because I don't think you guys can do it, but we won't have that more complicated. So drop down to number 4. That fifth power gets a little ugly. I don't know. In fact, very common thing that happens to people is the order that you guys put these in. Always go from smallest to biggest. Always work from left to right. You've got to look. What's going on? What did I do? Johnny, what are you thinking? Are you sure it wasn't me? Does anybody agree with me? You do. Okay, good, good. Okay. Always go from left to right. Again, I want to point out this terminology here. This is the proper way to write the second derivative when we do the dy dx form. It is taking the derivative twice on y with respect to x for the second time. That's how I translated it. And if it was a third derivative, I do d3y dx to the third, a fourth derivative, etc. It goes there. Also notice lazy. Sometimes I'll just do a y instead of a dy dx, and I just write that as y double prime. This is my y double prime chart. This tells the world I'm looking for points of inflection, and then I interpret it as my concave up and concave down. Okay? So, what should we do for homework?